Eddy current testing is the first of the techniques we're getting into where visual inspection and not a visual pre-inspection, not an initial visual or detailed visual inspection, but rather visual inspection of the non-destructive test process no longer occurs. So what I mean by that is when we did borescopes or different scopes, video scopes and whatnot, we did visually, we looked at it and had to identify what was wrong. When we did magnetic particle, we had to look for, visually inspect it for evidence of cracks. And when we do liquid penetrant, we have to visually look at and interpret. For eddy current testing, as well as the others we're going to talk about after this, ultrasonic, infrared thermography, and majority of the other techniques we're going to look at, it's going to have some kind of a readout on a display screen rather than a visual inspection. And I realize that like a video scope is a display screen, but you can think of the video scope as it's transferring what you would see here over to here. Okay. This is not transferring the image that we have to look at. We're looking for some kind of an indication on a display screen. And so it's a little bit more, I would say, theoretical and a little bit more, it's not something you can like look at and see as much. Part of that is we're finding things that we may not be able to see. Either they're too small to be tested using one of the other methods, or we're testing a material that doesn't lend itself well to any of the other methods we've talked about so far, such as like composites, or we're looking for something underneath the surface that's not necessarily visible right at the surface. Okay? So for eddy current testing, its uses, it's useful for crack detection. Okay, primarily, this is very common in aerospace and aviation. Majority of the time it's for surface cracks, but you can sometimes, there are applications where you can find subsurface cracks, shallow subsurface defects, up to about a ½ inch deep at the max. Okay. The other thing we can find is corrosion detection, and this can be, it's useful because it can find what's called thinning or backside corrosion detection, so especially on things like sheet metal. And where you have like a lap splice, two pieces of metal, right? The corrosion tends to form between the two pieces of metal. An eddy current test is able to pick up that corrosion that might be occurring, between two pieces of metal that are riveted together, or on the backside of a piece of metal where you can't access the inside of it. The applications for that primarily are more oil and gas industry or things like that, where like the inside of pipes can be either corroded, or they can actually the walls can be eroded away if there's some kind of a material like oil that contains sand or other crud in it before it's refined. Those can actually thin out, they can grind out from the inside of the pipe. We can also do things like material coating, okay? The probes we use, the distance the probe is from the surface of the metal will affect the readout we get. And so if you have paints or other surface coatings, that, if they change in thickness, it's going to move that probe closer, further away from that metal surface. And so you're able to measure that. So things like paints, chromes, claddings, platings. Material identifications, we can check for conductivity, different types of conductivity, which allow us to do things like alloy sorting, as well as heat treatment and case depth measurement. Okay? The way eddy currents form, they will form differently in a piece of heat-treated metal than a piece of non-heat treated metal. And so if there's a difference in thickness in that exterior, especially case hardened or case where you heat treat the outside but leave the inside not, you can actually measure how thick that heat treating is, how thick it penetrated, or nitriding, or different processes like that. Advantages are it's very sensitive to small cracks and other defects. It's extremely sensitive. It can detect surface and near surface. You get immediate results. You're watching the screen as you're going, and you immediately see the results. There's no dwell times. There's no things like that. It's very portable. The testers nowadays are very lightweight, portable. You can carry them with you without having to do that. There are bench versions too for doing high volume applications. It can do that more than flaw detection, as we saw in the previous slide. It's got other uses. It can be, one I don't have here, is it can be automated. There are automated eddy current test systems out there. And even the portable systems have the ability to provide some type of automated indication, audible or visual, in addition to just seeing the readout on the display screen. Because when you're using this to test the skin for cracks around every single rivet on a lap splice, so lap splice that runs from the nose of the tail to the nose of the aircraft to the tail of the aircraft, and is 6 rivets wide, and there's a rivet every inch. So you can think about, there's a lot of rivets that you have to do. You might get a little bit, you kind of go into a bit of a daze as you're sitting there running a probe around each and every single rivet. Having something that gets your attention, if it finds something, it probably would be helpful. I've seen an inspector had a ladder on the wing, 4-foot ladder, was sitting on top of the 4-foot ladder, did not have fall protection on, was doing eddy current testing, had his probe up here, had the display here, and he fell asleep like this, sitting on the top step of a ladder, on top of a wing, with no fall protection, sleeping, leaned on the side of the plane. And when we saw that, we were all afraid that if we tried to wake him up, he would startle and everything would come crashing down, so we really didn't know what to do. Lynn was safe. We got him down safely. He went and took his lunchtime nap in the parking lot that he did every night, and we were all good. Minimal part preparation is required. As I mentioned before, it can be done, it can actually be used to find like paint thickness and that. So typically you don't have to remove any kind of paints or coatings. So again, fuselage, airplane in operation, you don't want to have to strip the paint every time you do an inspection for rivet cracking. So that's where it has like an advantage over, that's why we wouldn't do like dye penetrant on all those rivet lines. And then finally, the test probe doesn't need to be in contact with the part. In fact, technically, when you're doing it on the outside of paint, paint does not, you are not picking up the paint, you're picking up the metal underneath the paint. The probe actually never does touch the metal that you're checking, right? And it can actually be, if you can hold it a consistent distance away, you don't even need to touch the part. So there are air-gapped versions. Some of the limitations, this has to be, because we're talking about eddy currents, currents are electricity, our part has to be conductive. So it can't be a composite, typically. Surface must be accessible. I say typically because there are metal composites, and you could, in theory, do it on a metallic composite. But again, mainly used on things like sheet metals and structural metals. So surface has to be accessible. At least one surface does have to be accessible, right? And the contrast to that, everything so far we've had to be able to access. The example I gave where it doesn't have to necessarily be accessible is like X-ray. You can think of, you can inspect your bones in your body without having to pull your bones out of your body, right? So it doesn't have to be, this in case, it does have to be accessible enough that the probe can get nearby or touch the surface. It does require a certain amount of skill and training, especially for setup and identifying how, identifying a flaw or a true indication versus an irrelevant indication or a false indication, okay? And the surface finish or roughness can interfere with it. So because it is so sensitive, when you're moving a probe around a surface, if you have a rough surface and it causes it to wobble or anything like that, that'll actually show up as a false or non-relevant indication, depending on how you want to talk about it. Just because it is so sensitive, just a little bit of movement in your probe in relation to the surface is going to cause some kind of indication. You have to have reference standards before you start. That means you have to have something to compare it against. You have to have a known good and a known bad, so that when you go and test your part, you can tell, is it good or bad? Okay? Now, the standard isn't necessarily an entire airplane where you know the status of everything, but it might be, a lap splice made out of some pieces of sheet metal, similar to what's on your aircraft, where there is one rivet hole that is good, doesn't have any kind of crack. A second rivet hole has a simulated crack in it. So you can test that, make sure your machine's set up correctly, see what the indications are, and then go do every single rivet on the aircraft. Okay. Or the root of your fan blades, if you're doing a CF30 or a CF6 engine, the ones on the 737s and A320s that have fan blade issues. They use this a lot to check those. The last part, depth of penetration is limited. So I said it can do surface and shallow subsurface flaws. Again, limited to about a half an inch. Some of your pipeline stuff can do like real thick walled pipes, like 1 inch thick pipes. But at that point, you're starting to move more into what's called ultrasonic testing territory for getting that deeper penetration. So this really, half inch or less is typically where it's used. There's some fundamentals here. It's based on electromagnetism, and because it's really hard to describe and show, I'm just going to show some videos real quick. So this, though, is based on the principle of electromagnetic induction, and that is we take a coil, we run an alternating current through it. That coil is going to create a magnetic field. That magnetic field is then going to actually go into our part, create a current in the part, and we're going to measure that current that it forms. And so I'll show you some videos on that real quick here. So here's the pictures of it. So inductive circuit, we're going to have a voltage source with AC, a coil of wire as our conductor, and that's going to create that that magnetic field there. Okay. But what happens though, when we create that magnetic field, as that magnetic field builds, right, we're going to send our current one way. That magnetic field, as it builds, it's going to start to oppose the flow of current. Right? There's going to be a certain amount of, and the way that field builds will affect how much pushback it creates, how much it impedes the flow of currents, or it causes impedance. So with an inductive circuit, just a quick review of hopefully electrical 1, maybe. You learned about inductors. So inductors create that impedance in 2 ways. The first is purely inductance. So the current carrying coil that produces that magnetic field produces its own current flow, its own kind of, reverse current flow from the magnetic field acting on the coil after it's built up. And an AC current that's constantly going to be flipping, so there's going to be a delay. The other thing is that inductance has a certain amount of inductive reactance in that it is not aligned perfectly. It's not perfectly opposite of the current that's coming through, but rather, if you look at a sine wave of it, it's 90 degrees off. So it's not going to impede all current flow, right? It's going to be a portion of that current flow, the vector portion that lines up with the original current direction, or that opposes the original current direction. The portion of that inductive reactance that's out of phase, that's 90 degrees to it, isn't going to do anything to affect it. So you're still going to get a positive current flow. It's just going to push back and reduce it once that magnetic field builds up. And that's what creates impedance. So it's the vector sum of the inductive reactance and the resistance, right? Just the wire itself is going to have a certain amount of resistance in the coil and gives you the total resistance of the coil. And that's inductance. So inductance is in henries, reactance is in ohms, but it's not your normal ohm symbol, it's X sub L. So ohms due to henries. And then impedance is also called an ohm, but it uses that symbol Z. So you've probably seen the Z for impedance. Sorry, inductive reactance in your, Z for impedance in your electrical class, right? So how does that work? Here is your standard resistance. So in a resistive circuit, right, if our voltage, if we have a higher current, it's going to push back on the voltage just because the resistance of the electrons flowing through the wire. It's going to slow down or it's going to, again, push back on those. Right? So the coil of wire itself is going to have a certain amount of resistance like a resistor. But here is where that inductive reactance comes in. It's 90 degrees off. So here, the voltage is here, but the current is not going to, right here you can see the current stays in phase with the voltage. So voltage increases positive, the current increases positive. And then when it peaks, they both peak together and come down. Due to the inductive reactance, which is caused by that field collapsing, forming and collapsing, you can see here the current is actually going to be slowed down by 90 degrees, or half of a side of the phase. So impedance is that total of resistance in an inductive circuit. If we add together inductive reactance and resistance, we get our total impedance. And so just if we look at it visually, here's how we can visualize it on a graph. So if we put our resistance down here at the bottom, our inductive reactance being 90 degrees off, we can put it 90 degrees to it. The total impedance is this arrow here. You can see it's not the sum, it's not just R plus I, or Xi. You can't just add them together, right? This total length, to find this length, essentially you have to use Pythagorean theorem, right? A squared, resistance squared, plus inductive reactance squared equals the impedance squared. So why is this important for this? Well, our display on our eddy current tester effectively is this XY impedance plane. Now, it's not always perfectly, inductive reactance isn't always vertical. Resistance isn't always horizontal. In fact, when we go to our display, one of the settings you can change is you can rotate the whole display. So you can rotate it any direction you want. There's kind of standard directions you normally would do. When you're doing a crack check like shown here, you typically put your origin at the lower right because it's going to go up and to the left. So really right now if our origin's normally at the bottom left, we've rotated this thing like 180 degrees because that would be top right. It's kind of rotated, Again, it really doesn't matter. It's not mirrored, it's rotated, and it's not doing a straight line, okay? So you can't think of it as showing just that, but it doesn't, again, inductive reactance isn't always up and down, and, resistance isn't always left and right. It's just we rotate it whatever we want. But to get the point is as we move our probe, and as these two items change, this point right here is going to move. And so what you're seeing, the tip of the impedance line is going to move. So what you're seeing is as we've gone over 3 different cracks here, that impedance line, this draws that point over time. It's not drawing this and this to get to this. It's not drawing this line. It's drawing this point at the tip of the impedance line as it changes. So you can think of it as if we increased resistance and inductive reactance and this line tip moved from the origin up to here. Okay, that's what these lines are. It's just showing where the tip of that impedance is, or what the total impedance is. So it plots that resistive vector. The eddy current tester in the probe is monitoring that coil that's in the probe. It's monitoring what its resistance is, what its inductive reactance is, and then it's giving you essentially where the impedance ends up over time. So each of these is what happened is a probe was moved along a part, and as we went over a small crack, it went up and down. As we went over a bigger crack, it went up and down. As we went over the biggest crack, it went way up and down. You're going to do this same check. You're going to find this identical type of indication with either our test blocks either have 3 or 4 cracks in them. Just depends on the test block you grab when you do it. So it shows that path of changing vector sums. It doesn't show the vector sum. It doesn't show the resistance. It doesn't show the inductive reactance. It shows where the impedance is over time. Now we can get into some of the theory. Here's the videos that I wanted to show you.